this is the first course of our introduction to Lean. And the target of this course is to just get to hands-on the Lean 4 and help you to formalize some statements and prove some theorems at the fastest pace possible. So I think the first course is going to be very short and the content is not very full. So if you have some questions, you can break me at once and I can answer for you. Yeah, so that's a simple introduction. So first, the problem is why we use Lean to formalize statements. The first thing that Lean is an interactive proof assistant. It has a verifiable statements and proofs. It's completely equivalent to logic reasoning. I will explain later. And second is that it has a modern friendly interface and it has the largest community in the world. At least at this time period, Lean is the most famous formal proof verifier in the world. And second, Lean is based on dependent type theory. This is a specific branch of type theory. I will later explain to you why it is called type theory and why it is called dependent type theory. The first is that this correspondence is what we call Curry-Howard isomorphism, which says that when we use the functional programming language like Lean, which means when we write statements in Lean or we write theorems in Lean, we actually do it in a programming way. So this isomorphism makes sure that when we do it in the programming way, it's actually completely equivalent to the logic reasoning, which means if we finish a program and it can halt, it can give a correct result, it is equivalent to be logic correct, which is very important in mathematics. So why is this important? So for students in your education experience in the past, there are always times like some teacher tell you that your proof or your solution is not correct. You may skip some step in your proof. So this makes us annoying, right? Because we think we get the correct proof, but he will maybe ask you to explain why this proof work, why this step is correct. But the natural language is always not so accurate. But if we can express it using logic, we can make sure that our statement is true or correct in whatever time and whatever space. So this is a good point or an advantage of logic reasoning or the formal verification. And another reason why some people in the company, for example, in the Huawei or in the other company, there's many companies are currently doing Lean. So why they are doing this? Because at the current time stage, people use LLM to process information and to generate contents. Or for example, if you are doing your homework, you are likely to use ChatGPT or use DeepSeek to generate proofs. But from time to time, the LLM can always make some minor mistakes, which is hard for people to discover. So if we have the capability to transfer the since Lean is a language or formal language and natural language is also a language. If we can make a conversion between natural language and formal language, we can actually verify whether LLM is give the correct result, which will benefit the LLM reasoning or the language model reasoning. Yeah. So this is why we need to use Lean currently at this time stage. So why we choose Lean instead of other proof system, which we can see like mathematicians are developing proof systems a very long time ago, since maybe 1960s. This is a very primitive proof systems. It's a coq in a very earlier stage, and now it looks very different. But in the earlier stage, it looks like this. But this is how Lean proof looks like. The difference that the coq only support ASCII2, and the Lean support Unicode, which makes which makes it easier to type mathematical statement. For example, we want to type a real number, real field, and complex field. It's very convenient to do things like this in Vim. So it will further simplify your statement. Will make it very analogous to natural language proof. And with the interactive prover, which means every several proof step will correspond to some formal of some natural language proof step. So this kind of proof stage make it more similar to natural language proof. So we can actually do the translation. If we want to do the translation by LLM, we can do the translation more easier, and the learning curve is less steep than the traditional proof assistant. So this is why we choose Lin. And the final reason why we choose Lin is that Lin is currently have the largest mass repository in the world. I remember that last time I gave a presentation in AUS that the theorem is only about 150,000, and only several months, about 3 months past, it has added about 30,000 theorems and add about 20,000 definitions. So it is expanding very quickly. We can see from the curve is the theorem and the repository is expand rapidly. We can also see from the dependency graph. The dependency graph is like when we formalize some kind of mathematical statements, we need to depend on some previous mathematical object we have defined. For example, we want to define ring, we have to first define group. To define group, we have to first define monoid. So this will result in a dependency graph. So this dependency graph shows how in all the mathematics branches, how the theorem is scattered. We can see that although many theorems are in algebra, but in general, we have some theorems for all kinds of mathematical branches. So if you are doing math at different levels, at different aspects, you can always find the thing you want, likely in MathLib. So, but in other words, the size of the MathLib also make the search of theorem harder. So later we'll talk about some solution to semantically search for theorems. So to start our tutorial, we will first introduce some basic syntax in Lin. So which is first associated with type and values, because Lin is in essence a type system. So each value, the criterion is that each value is associated with a type. Although sometimes you don't do it explicitly, but in the compiler side, it will assign a type for you. For example, things like since everything has a type, things like natural number, integers, and rational numbers, real numbers, their type is this big type, and you can define elements of such as natural numbers and integers. That's how we define natural numbers and rational number of this. The syntax is that before this comma or this how to spell before this symbol we have the value, and after this symbol we will have a type. This is all the basic syntax. So actually we can do a variable statement in this form. But in the different type we have very different calculation principles or have very different properties. For example, we check in natural number, we will get some kind of unexpected behavior. For example, we do the division, it will show it is 0 because you cannot actually do the division in natural number. So it will give a 0 question mark. For example, it's similar to Python. If you type a percentage, it will give you just a modular. And you can also check this 2 minus 3 statement. Is this maybe most confusing things for the beginners, because the 2 minus 3 will give you 0, because minus negative part is not in the natural number. This is how Lin deal with this kind of issue. But if you are in other fields, everything looks fine. Yes, this is how type system work for in Ling. And another thing is that you can use old types to construct new types. So for example, we have some basic type like the natural number, integers, and we can actually define new types. The type natural number and the right arrow, then natural number, this identifies as a function. So you input a natural number and output is the natural number. And we also have product types, which the element of this type is just a tuple of two elements. Both of them are real number, and you will have finite set natural number, which means a finite set with all the elements is natural number. So this is how you use old types to define new types. So we can check all this type. We'll find they are all new types that we have defined. So in the previous two slides, we have talked about how to define types of the blue big type. But another category in Ling of a type system is prop. And values of type prop is what we call propositions. This is sometimes very confusing for beginners, but later I will use some examples to demonstrate this. Propositions are of type prop. And when you provide a value for the proposition, for example, if we provide a value of this type, we actually approve this proposition. So I will take this as an example. So this is the symbol. The before is this, what is this variable? And we declare that this variable is of this type. This type is a proposition. Note that this proposition is of top. And if we provide a value for this type, then we get it proved. This is how type system works. It looks confusing in the first place, but later I will use example to explain. So I think it's time to do some demonstration. So in this course, I will use this platform for demonstration. So for people just register and have been added to this project, you can actually log in at this time. Let's try if you can log into this page. I will close something of this. Since we are dealing with syntax, we are using this file. So I can already see some of your symbol indicates that you have entered the project, so it's fine. So the first thing we have to deal with is that we can check the type of the natural number. Of course, it gives a natural number, but in this case, we can see that we didn't assign a type in this case because the Ling has by default infer the type of this expression. It will infer it as a natural number. But for example, if we type 2 plus 2.0, of course 2.0 is a float, but 2 is a natural number. We can not actually do add between natural number and float. So in Ling, it will automatically transfer to the float and add two floats together. And this is how dependent type works, which means the type of your expression, for example, this 2 is depend on other values. Because if you input other values here, it will become other types inferred from this expression. So this is called dependent type theory. This feature in Ling, just like some dynamic type in Python, this feature make it available that we can just type more expression without declaring its type, and the in the backend link will get it right. So this is a very convenient to have dependent type. So this is what all we have talked about. If we want to check the type of a value, we use check. But if we want to use evaluate the value of the expression, we use the key eval, which will give us the value of this. So so we can say that the rational number can be evaluated, but for another case, if we want to evaluate a real number, for example, if I type 2 real, this may be this is available, but if we want to evaluate this, it will say that it failed to compile definition. So why did this happen? This is because real number is not in a sense computable. It has arbitrary accuracy. So it's not a computable thing. So you cannot just evaluate what it is. So if you want to evaluate, you need to transfer it into another type that is in a sense computable. But this is what it will not affect that you can actually prove something, because the computable word and the propositional word is two separate words in math. It will not affect your theorem derivation. So I will just delete this line. So the first syntax is that how we can define values in a formal way. So for example, I can define my favorite number is 2, or I will check number to 43. And you can actually type another variable called your favorite number. So anyone can help me type this number? You can try. I don't know whether multi addition will make it collapse, so we can try. Yeah. Oh, it's a large number. Okay. So it's fine, and so we then have another variable called your favorite number. It's fine. So this is how we do the definition. The before this symbol is the variable name, and after this symbol is the type you specify for this variable, and then you give the value. So if we do the check, for example, your favorite number, it will give us a natural number, and if we do the evaluation, it will give the value. This is how we define expressions in Lin. So the next few step is that how we define new types out of the old types. We have just specified natural number, a real number, and a function from natural number to real number. For those high school problems, we can identify this function. You can, in one way interpretation, you can interpret this as from the function between natural number to the real number. Another way is that you can identify this as a series, because the index is on the natural number. So this is actually also a series of this type, and it's very different from what we would define series in day-to-day life. So now we have this type, we can define type of values of this type. For example, we have find set A. We can use this notation to define find set, and we'll have another find set, and we will also know a find set. Since it's finite, it's of course computable, so we can do the evaluation on it. And for a set, it's the same notation, but of different type. For example, both of them were contains 1 and 2, but one is set, one is a find set. If we do the evaluation on set, I think it will complain. Yeah, it will complain that set do not have a computable representation. And if you do it with find set, and you will get the answer. So since we have the value for this type, we have the expression for this type, we can do some simple computation. For example, the union and the intersection operation. For example, we have set A and set B. We do the union, and we find that this union operation still yields a set of natural number. Yeah, two sets. The union of two sets is still a set. And since we have find set, we can evaluate this kind of statement. If we evaluate this find set A union find set B, we will get the 1, 2, 3 contents in the set. We can also try another way, which is intersection. It will get the correct answer. So this is how you can compute things in Ling. So it's the same with list. List is also computable, so we can evaluate. So this is all for the old type to define new types. So another important thing is that we need to define functions in Ling. Functions is one of the it's also an important object in Ling. So to define functions, one way is that we first identify its type. It's a natural number to natural number type, and we use fun this keyword to specify this function. This if you have learned logic or something, it's also called lambda abstraction. For example, a more classical demonstration in some logic book will be like lambda. This will also be fine. So, but in Ling4, we prefer this fun keyword. So another way, or a more common way, is use the bracket to define functions. This is quite like what you would expect in normal programming language. We use a bracket to specify the params, and use the type to specify its output type, and give the value. Yeah, so we can always define a function of other type. For example, f real. This of course is a function type. So these two are all function, but of different types. So the next demonstration is propositions. So propositions is how the basic elements you need to construct a mathematical statement. I will zoom out for a little bit.
Option x plus 3, natural. We put x minus 3, will you complete one?
Sorry, x minus 3. Yeah, it will not complete. The subtraction will always work, because if you get the minus number, it will get to 0.
Okay.
Another, I think your problem is actually if we give another type. If you end up with another type, what will happen? For example, we can do some division. I think division is also good. Yeah, it still yields a natural number. But if you really end up with another type, for example, you delete this type declaration, and if you get a real number, it will do the auto conversion to convert the natural number to the real number. Yeah, so here's how dependent type system work. So let's get back. The most important thing is the propositions. So you can actually define proposition. Proposition is like saying that you can say whether it is true or false. And since that you can say it is true or false, it's called propositions. So the proposition can have many kinds. For example, we have this very simple equality. We can say it is true or it is false. So when we define things like that, it will have a type called prop. It is in the prop world. Another simple one is that it's what you just input your favorite number. We can also define this kind of proposition, which says that your favorite number is not equal to my favorite number. It's also a proposition.
I also can define the proposition like 2 plus 2 equals to 5.
Yeah, of course. This proposition is not true, but it's also valid. Yeah, you will later decide whether this proposition is true or false. And this is a very simple proposition. And for the medium proposition, you can use quantifiers and some logic connectors. For example, you can use AND as logic connectors. It's similar to mathematics textbook. And the quantifier is like this. But in addition to set theory things, or in addition to normal logic textbook, that you have to specify a real number, a type in this case to get this work. You can also choose not to add this thing, but it will do the auto conversion, say that it is Z is of integers, which is not what we want. So now we need to accurately specify what it is. So for harder part, we can use many different logic connector and quantifier to get a more complex proof. For example, we have we'll have this symbol identify the implication, which means proposition A can imply proposition B symbol. This helps us construct more complex propositions. So we can check this. Not this one. We can check this. We will get not this one. Sorry. We can check this. We will get its type is a prop. So now we have definition for prop. How can we define a mathematical statement? So mathematical statement is like this. We define the name or variable for these statements, and we specify a type is a easy prop. Note that the easy prop, the type of easy prop is a prop. But when we define like this, we want to define theorem. Its type is of easy prop. This is a very different thing. You can check. The type of easy prop is a prop, and the type of easy is of easy prop. It's like a hierarchy structure. So how can you prove this thing? You specify the value of easy prop, of type easy prop. If you can specify a value of this proposition, we say that you prove this mathematical statement. Yeah, this is how you get things work in Lean. Any questions? Because I think this part is a bit confusing. You can understand this part. Okay, I will use later. I will use a more simple graph to say this thing, to demonstrate this thing. So we have the proposition type. Actually, we can use the proposition to define more complex a mathematical object. For example, in this thing, let me manually type this. In this thing, in mathematics, we often have a statement like this, right? This is what we call a set comprehension in mathematics. So in Lean, we also have this kind of syntax. We just do it in a similar way, but we use the logical connectors. X cubic is less than 5. So this is how we define a set comprehension. It's very similar to what we would expect to the textbook. Its type is a set R, set of real number. So there's some more harder mathematical statements. For example, before we had defined the epsilon delta language for functions. This is what you will have learned in the undergraduate calculus book. So if we want to actually this kind of proposition, you can also have the parameters. you can apprehend it as a function. When you input the parameters, it will output a prop. So how can we specify a statement that what the f real function we have defined has a limit at 0.3. We can feed in all the parameters f real and the point of x and limits into this function to know that this thing is a prop. And we define a variable of this proposition type. We actually define a theorem. So this theorem is a little bit harder for us. It's a little bit hard for us, so I won't prove it here. So actually, just to demonstrate how you can define a proposition, how you can define a theorem. So another more clear way, or the way you see most common in MathLib is like this. You can have a proposition type from here. This is the proposition you want, and you define some parameter. This can be seen as the variable you need, and the conclusion you need. And you compare these two things, you will get a statement. So it's quite simple. So in addition to this, not only you can input variables as the parameters, you can also input other propositions as parameters, which means when you have some assumption, under these assumptions, you can get the conclusion. So this is how it works. So I will use a very simple Gaokao problem, which is Chinese university entrance examinations. I will use this problem to demonstrate how I can define a statement for this. So suppose that A equals, we have a set A and set B. So first we define the variables we need. Let's call it a theorem. Theorem is just an alias for definitions. So for you, if you don't know, let's call it name called test set. Not test set, it's weird name. Set test. And the variable is, for example, A and B. They are of set R. Sorry. And next, we need to input the assumptions. So what the assumptions we would expect is that a two equality, A equals and B equals. So now we can input this kind of two equalities. Let's input this. The first one is HA. The equality is A equals. We can just, since we have already defined this in the previous step, we just need to copy it. Oh, I believe I need a new name. And another assumption is that the declaration for B. So HB is B equals, what is this? -1, 0, 2, 3. And we have all our assumptions prepared. Now we need to derive the things we want to get. We want to get the A union B equals -1 and 0. So it is to declare that this variable is of this type. So now we can explicitly type this equals -1 and 0. And since we do not have a capability to prove this, we will specify the value as sorry. So this is how we finish a statement. So I also give you another Gaokao problem. I will give you maybe 2 minutes so that you can try this statements on your own project file. You can create a new theorem like this so that everybody can see. Okay, so I think the time is fine. So I say, have anyone formalized this statement? No one has typed the answer. I'm not sure. Yeah, I think somebody has done it. So you can keep it this way. I will fix it for you if it is not compiled. Is it compiled? Does it compile? Let me try. It is not compiled because you need to input Unicode. Who did this thing? Who did this thing? Okay, thank you. You need to input the Unicode. So how you input Unicode is that if, for example, you want to type alpha, you type your slash and A, and you can type the space to get the Unicode. So for beta, it's the same thing. Yeah. I think this works fine. Maybe I need to import I think I need to import a new thing because in this context, it doesn't know what sine cosine is. So I need a new import. So and wait a minute to see whether this can compile. So here sine cosine is a function. So in addition, you need to type a space between functions as a function parameter. Okay, let's wait a minute, see whether it compiles. Maybe I need to press restart file. Maybe wait 1 more minute. If it doesn't work, I will swap to VS Code. So did it work? So I will check VS Code to identify this. So here you define a theorem of this type. The theorem will look like this. You input all the assumptions and you input the type. Then you will get your first statement in ling. This is very simple. So this is also a very good problem. So we will try to prove this problem in the next time. I don't think we will have enough time in this lecture to prove this. So maybe some content I will leave to next lecture. So I will continue to tell you how we can prove things in ling. Let's try. So here's what a normal proof in your education experience you will expect. Maybe in some time you will see improve things in this way. First you have some assumptions, and then you apply some theorem. Use theorem 1, you will get a different goal, and use theorem 2, you will get a different goal, and use theorem 3, you get the goal you want. And maybe this is the statement. This is the proposition you want to prove. And here, such a chain helps you close the goal or helps you finish the proof. So it's very similar in ling in this case. You have several types. Instead of goal, you have several types or several propositions, and you use theorems or functions which include a proposition and output the propositions to connect these different propositions. And finally, you get what you will expect of the final output goal. So One way, of course, you can directly construct all these theorems together in one time and compose all these functions together to get the type you expect. Is what you would expect if you have do the programming language like Python. But the first way is, of course, what I would expect to give everything in one line, to compose the different functions, the trans function, associative function, commutative function, together to get the type you would expect. And another way, this is what we call a term proof. It's like you use theorems to directly get the type you want. Another way is featured by Lin or of our preference is to do a step-by-step proof. This is called attractive mode. So what attractive mode does, instead of just proof from theorem 1 to theorem 3 from up to n, maybe you first figure out how to prove from type 2 to target. Or you have first figure out how to prove from type 1 to type 2. And you combine these two parts, you will get the final proof. So this is how Active will help you to split the chain into a shorter chain and get the proof right. So this is how we do it now. We use several tactics and text sequence to close the goal. So actually there's over 300 different tactics in Lean. So I have classified into different levels. First of all, I have some very basic tactics, which do very simple things, like just rewrite something or apply a theorem to just like split the chain. We also have some medium advanced tactics. They will use some rule-based strategy to search or try to simplify expression and help you to get the goal. So this was how this was some more advanced tactics to do this. And there's also some super tactics, which means use some beam search or proof search system to iteratively try all the possible tactics and like exhaust the search space and get you directly into the goal. So I put a question mark here because now we have something new to do this, which is LLM. You can actually use LLM to construct new tactics to get to the goal faster. This is what I will show later. So another problem is that when you prove something, you need to find all these theorems to use. So it's actually very exhaustive to find all these theorems because there's so many theorems in MathLib in different names. So how do we tackle this? We have a link search system to semantically search what we would expect out of the MathLib. For example, in this case, if we type a statement in natural language, it will yield us a theorems in MathLib that looks more similar. I will tell you later. So this is basically how you finish the proof. So now I will demonstrate you some most basic thing about proving thing. So I will switch to another file called calculation. And for the reference, I put this theorem at the top. You will expect to prove this theorem after these several courses. The first, of course, is to give the proof directly. We have, for example, RFL is a theorem which states that x equals to x. This is a classical proof by reflexibility, which means an object is equal to itself. It's kind of axioms. So you can also use a much non-trivial thing like mode association. For example, if you have a statement like this, you want to prove. So you check this type, you'll find that this is exactly what you want. So you can just type mu association, and you will get the proof. And of course, here's directly when we want to directly get a proof, when the proof state is very long, it's very annoying to write such long terms. So we need to split up. So how to enter the step-by-step mode or tactic mode is that we use the by strategy, and this by strategy will give us into a tactic mode. And now the first tactic you will see is exact. So exact means that you find what you want and you just know this is what you want to prove, and you can prompt exact. And as we see, REFO is also a tactic which is a simplification version for exact REFO. Use this reflexibility. So instead of just prompt all the proof term, we can do it in a much smarter way to prove this. For example, for this theorem, we want to prove this is equality. We first notice that we need to swap the order of several variables. So we use rewrite tactic. For example, we write mo also associate, and we can see that not to swap the order, but to swap the connection of symbol, connection of multiplication. So we can see that B and C were grouped. And in this case, we just need to swap the B multiplication with C and A. We need to swap this position. This is what we expect as a mo commutative. And after we swap the order of these two terms, we actually get what we want. And this time is the old tricks, right? It's just a REFO thing, because it just states A equals to A. And now we can use REFO to close this goal. So this is very simple case which we have done. So actually the rewrite tactic, what the rewrite tactic does is that we have some kind of equality, and we use this equality to match the patterns in this goal. And just directly replace this pattern with the equality. This is how we change the type of the goal. And more convenient way is that we use RW. RW means that we use write immediately followed by RFL. So rewrite is a combined tactic, combine rewrite and RFL, and we just need 2 lines to finish this goal. So this is cool. We also have more complex proof. We use several rewrite sequences. Another feature of RW is that we can use this arrow means we change the right hand side and left hand side. If we want to rewrite, for example, at this stage, we actually want to replace the B and F to extract B and F and make it to extract the bracket. So we use the inverse order of rewrite, and we can get things right. So this is how rewrite goes. So I think this is all for the first course, because I think the time has exceeding. So in the next, I will leave, in this course, we will already introduce the rewrite tactic and REFO tactic and exact tactic. This is the 3 tactics we have learned in this course. And for the syntax part, we have learned how to define variable, how to formalize statements. So for the next part, the more advanced tactic, for example, cock, ring, and thing, I will leave to the course 2. So since we have already learned how to formalize a statement, I will now introduce the first AI tool or LLM tool available for our capstone students. So I will swap to the VS Code, because this platform does not support this tactic operation. For example, still in the syntax. Here, since we may want to prove this, we want to formalize this formal statement. So sometimes it is annoying to write it on our own, or if we are lazy. So we can use this word, this keyword, and just prompt all thing here. And in the right-hand side, we'll get all the possible formalization result. This is done only by input your informal statement, and you will get out of the formal statement. So how this is done? This is done by extraction all the mathlib data and do the inverse translation, and we do the supervised fine-tuning and some augmentation techniques on a large language model, for example, DeepSeek Prover or Llama. And this is what we get a very good model who is very expert, or even more expertise than me or the other link formalizers. It can do the formalization very well. For example, I didn't check the correctness of this statement. I just press randomly, so it gets the right formalized result. So we can, it's the formalized in the mathematical side is also correct. It does not get things wrong. It also fill in the proper namespace. It opens the correct namespace. So if sometimes you do not know how to formalize some statement, you can actually use this tactic. So since this tactic is based on large language model backend, so it's still on the experimental stage. So it is only available for the capstone students. So maybe that is all for today. There's also some proof things we didn't go through, but we will leave you to the next course.